welcome to Matrix. My name is Looney and today we'll be doing your exam prep for maths. I'll be assisting you to get all of your questions and comments through to us, so all you need to do is follow Matrix on all of our social media platforms, check us out on our WhatsApp line, and if you miss any of our videos, they are available on YouTube. All of the details are on the screen. As always guys, we've got a cool competition going on for you, so do stay tuned to get all of those details. I'm not alone. I've got my favorite sign language interpreter with me, Nicolene, as well as our awesome teacher, Nicola. Thank you so much guys, and over to you.
Thank you so much, Looney. I really appreciate the introduction. And welcome everyone, welcome Matrix to your revision preparation for Mathematics Paper 1. We're going to go through quite a lot of material today. We're going to try our best. We're going to be doing a little bit of algebra, some sequences and series. We're going to be doing some functions, a little bit of calculus, and hopefully some probability at the end. So it's a lot to get through, so let's get started with the first question. Okay, so question 1. Show that the roots of x plus m times x plus n equals 3p squared are real for all values of m, n, and p. Okay, so this is a question that's asking us to look carefully at the roots and to understand the roots of this equation. Usually we understand the roots by looking at the discriminant. So really this is asking us to calculate the discriminant and then to critically look at the discriminant and see whether it is greater than or equal to 0 or whether it is less than 0. Okay, so we know that for the roots to be real, the discriminant needs to be greater than or equal to 0. So we need to calculate the value of that discriminant. In order to get the discriminant, we know that that is equal to b squared minus 4ac. So we need to be able to extract the b, the a, and the c from this expression. To do that, we need to get this into standard form. And we can see that at the moment, it is definitely not in standard form. We're going to have to multiply everything out on the left-hand side of the equation, and we are going to have to bring the 3p squared over to the left-hand side to get it into standard form. Don't forget that the variable in this is x, and m, n, and p are effectively constants. Okay, so let's start multiplying this out. We're going to FOIL, so we've got x squared, we've got plus nx, then our inner terms, we've got plus mx, and the last terms, we've got plus mn. And as I said, we're going to have to bring that 3p squared over to the other side, so it's going to become minus 3p squared, and that is all equal to 0. We've got two x terms here. We've got nx, and mx. So let's factorize the x out so that we can get the coefficient of x. So we're going to factorize the x out, and that leaves us with n plus m. Now, these two terms are effectively the constant in this expression. So we're going to keep those at the end, and that is the constant, which, as we know, is equivalent to c. Now that this expression or this equation is in standard form, we can extract the values of a, b, and c. So I'm just going to do it over here. We've got a is equal to 1. B, which is the coefficient of x, is equal to n plus m, and c is equal to mn minus 3p squared. Okay, so now to calculate the discriminant, I'm going to do b squared minus 4ac. It's very important to remember that this is asking us to show that the discriminant is greater than or equal to 0. We can't assume that it's greater than 0 to prove that it's greater than 0. So let's take this expression, calculate its value, and see if we can show that it's greater than 0. So we're going to sub in the values first. We've got n plus m squared, and we've got minus 4 times 1 times c, which is mn minus 3p squared. Okay, that is equal to n squared plus 2nm plus m squared, and then that's minus 4mn plus 12p squared. Okay, I'm going to go to the next page. Okay, so we had sorry, I have to go back. Okay, so we had n squared plus 2nm plus m squared minus 4mn plus 12p squared. Okay, so the easiest way to show that this is greater than or equal to 0 is to actually show that it's a perfect square. So we have two like terms over there, and we can simplify that to now be n squared minus 2nm, or mn, plus m squared, and then plus 12p squared. Okay, we can now factorize this into a perfect square. So we have n minus m all squared, and then we have plus 12p squared. So we can see that this final expression is made up of two perfect squares, and both of those perfect squares are always, by definition, greater than or equal to 0. So n minus m squared is greater than or equal to 0, and 12p squared is also greater than or equal to 0. So therefore, the sum of those two is also greater than or equal to 0. So we can say, therefore, the roots are real because the discriminant is greater than or equal to 0. Okay, let's go on to the next page. All right, so this is a question. This is a question about sequences and series, and let's read it together. 1.2. Given the series 1 plus 2 plus 3 plus and so on, all the way up to plus 5,000, write down the series in sigma notation if all the powers of 4 are removed from the series. Okay, so we're going to have to do this in two parts. We're going to have to find the sum of the first 1,000 natural terms, and then from that, we're going to have to subtract all the powers of 4. Okay, so let's first write just the 1 plus 2 plus 3 plus and so on, plus all the way to 5,000 in sigma notation. So that's going to be the sum as n equals 1 all the way up to 5,000 of n. So we can see that this is the sum of n going from 1 to 5,000 of n. From that, we're going to have to remove all the powers of 4. So if we think about the powers of 4, we need to be careful here. It's tempting to say that the first power of 4 is 4 to the 1, which is 4. But if we look carefully and think very carefully about it, we can see that the first power of 4 is actually 4 to the 0, which is equal to 1. So we now also need to think about what the biggest power of 4 that is less than 5,000 is. So we're going to have to go to our calculator for that. So let's try, if we do 4 to the power of 5, that gives us 1,024, which is less than 5,000. If we do 4 to the power of 6, which is going to be the 1,024 times 4, that takes us to 4,096. So in other words, 4 to the power of 6 is going to be the biggest power of 4 that is inside that series of numbers. Okay, so we can start getting an idea of how we can write the 1 plus the 4 to the power of 1 plus the 4 to the power of 2 plus, and that's going to go all the way to 4 to the power of 6. We can write that as the sum as n goes, or let's use a different variable here, as k goes from 1 up to, let's do 7, and that's going to be 4 to the power of k minus 1. Okay, so I wanted to use a natural number there, so I started at 1, I went up to 7, and we can see that each time we substitute that into the k, we're going to get 4 to the power of 0, then 4 to the power of 1, and so on. And the final answer, we're just going to subtract this sum from that sum. So I'm just going to put a big minus sign in between those. You can write it nice and neatly. So it's the sum of all the first 5,000 natural numbers minus all those powers of 4. Okay, so let's move on to question 1.3. So question 1.3 is about two converging geometric series. So we're given two of them, and as you can see, they're not numerical series, they're actually both in terms of x. So given that the following two geometric series are convergent, and there they are, the first one is 1 plus x squared and so on, all the way up to the end of time, all the way up to infinity and beyond. And the next one is 1 minus x plus x squared minus x cubed, also to infinity and beyond. Okay, so we're asked to determine the values of x for which the sum of those two series is equal to 8. Okay, so they're both infinite geometric series. So we can calculate the sum of each of those series separately. To do that, we're going to have to use our formula, which luckily you have on your formula sheet. So the sum to infinity of any geometric series is equal to a over 1 minus r, where a is the first term of the series and r is the ratio, the constant ratio from one term to the next. So if we look carefully at our first series, we can see that very obviously a is equal to 1. To get our ratio, we could probably just get it by looking at this one, but just to be sure, let's take term 2 and divide it by term 1. So we can do term 2 divided by term 1. And we can see that that is equal to, there's term 2 and there's term 1. So we have x over 1, which is equal to x. So therefore our ratio is equal to x. So we can already substitute into there. So a is equal to 1, and that is 1 over 1 minus. And for the ratio, we're going to sub the x into there. And that is the sum to infinity of our first geometric series. We're now going to do the same thing with the second geometric series. So again, sum to infinity of this series. So sum to infinity, we're going to use the same formula, which is a over 1 minus r. Okay, so for this series, a is equal to 1 again. Now we have to be a little bit careful. This is a series that goes positive, then negative, then positive, then negative. So it's going up and down before converging to a certain value. So our ratio is actually going to be negative here. So we're going to do term 2 over term 1, and that is negative x. This is the second term for this one over here. Let's do a different color. So this is term 2, the 1 is term 1. So we've got minus x over 1, which is negative x. Okay, so we know that our ratio, our common ratio for this is equal to negative x. So let's go to a new page to substitute that in. So we have the sum to infinity is equal to a over 1 minus r. And as we said, a is equal to 1, and for this one, r was equal to negative x. So therefore, the sum to infinity is going to be equal to 1 over 1 minus x, which is 1 over 1 plus x. Okay, so the last part of the sum is to now find the values of x for which those two series, or the two sums to infinity, equal 8. So that's what we're going to do next. So we're going to take the two sums to infinity and we're going to make them equal to x. So we have the first sum to infinity was 1 over 1 minus x, and the second is 1 over 1 plus x. And we're going to make that equal to 8. And now we're going to solve for x. So effectively, this becomes an equation with variables in the denominator. So as per usual, we're going to figure out what our lowest common denominator is. And in this case, it is actually going to be the product of the two denominators. So the first denominator is 1 plus x, or sorry, 1 minus x. The order doesn't really matter though, so that's cool. So we have 1 plus x and we have 1 minus x. So therefore, we're going to put everything over the same, oops, sorry about that. We're going to put everything over the same denominator. So we have 1 minus x, 1 plus x. And we're now going to multiply this numerator by 1 plus x, and we're going to multiply this numerator by 1 minus x. So we've got 1 times 1 plus x is just 1 plus x. And then we've got this plus, there it is, And then we got 1 minus x, and that is equal to 8. Okay, so the x's have cancelled each other out, as we can see. Plus x minus x gives us no x's, so those have disappeared. So all we left with in the numerator is the 1 plus the 1, which gives us the 2. And of course, we have the 1 minus x, 1 plus x in the denominator. And we can actually simplify that to 1 minus x squared if we multiply those out. And that is now equal to 8. Okay, we want to get rid of that denominator by multiplying both sides of the equation by the 1 minus x squared. So when we do it on the left side, well, we just left with a 2, and when we do it on the right side, we're going to multiply the 8 by the whole of 1 minus x squared. Okay, so to finish off, we're going to solve this quadratic equation. It's now become a quadratic equation. And we're going to release the x squared term from the bracket so we can move all our constants around and then solve for x. Okay, so we're going to multiply out. We get 8 minus 8x squared on that right-hand side. We can bring the minus 8x squared over to this side, and then that's going to become positive. And we can take the 2 over to the other side, and it's going to become negative. So on the right-hand side, we have 8 minus 2, which is 6. Okay, we can now divide both sides by 8. Therefore, we have x squared is equal to 6 over 8, which we can simplify to 3 over 4. And the very last step is that we need to now square root both sides. And don't forget, it's really important that when you take the square root of any number, you have both a positive and a negative root. And that's where you're getting your two solutions for the quadratic equation. So we're going to get plus minus the square root of 3 over 4. And we can actually take the square root of the 4. Obviously, the square root of 4 is 2. So we can just neaten that up a little, simplify that third into plus minus the square root of 3 at the top, and then, of course, your 2 at the bottom. And that is the final answer. So it's for those two values of x that the sum of those converging infinite series is equal to 8. Okay, so that's the end of this segment. So I'll hand back over to Luni.
Thank you, Nicola. Guys, we are going to take a quick break, but don't go anywhere. We'll see you straight after this.